Hello, today we're going to be talking about exponential functions. All right, so an exponential function is a function in the form of y equals ab to the x. We've actually seen a few things in this form, including geometric sequences, where b is greater than 0 and not equal to 1, and a is not equal to 0. If any of these conditions are true, meaning if b is equal to 1, or if a is equal to 0, or if b is less than 0, then it's not an exponential function. These have to be true in order for it to be an exponential function. Note that the variable x is in the exponent. That's why it's called exponential, because we have x in the exponent. All exponential functions of this form have the x-axis as the asymptote because y cannot equal 0. So you're going to see that asymptote in all of the ones that we're going to look at. All right, the coefficient a is the y-intercept. So coefficient a is the y-intercept. For example, in the problem we have right here, you can see it right here and right here. So we know that it's the y-intercept because if we are to enter 0 for x, we're going to get 3. If we're to look on the graph, when we look at where the function hits the y-axis, it's going to be 3. If we look inside of our equation, you can see the y equals ab to the x form. You see that a is 3, so 3 must be our y-intercept. Perfect. All right, the base, on the other hand, is the multiplier. The multiplier. So for each additional unit of x, so as we add 1 to x, the previous y value is multiplied by b. So you can see in our table here that we're multiplying by 2 every time because in the example equation right here, b is 2. It means that we are multiplying by 2 every time x gets bigger by 1. All right. So there are some things that we can look at the equation and kind of say, oh, I already recognize that my graph is going to look like this. For example, if our b values are greater than 1, the value of the function increases as x increases, and this is exponential growth. Whereas when b is between 0 and 1, the value of the function decreases as x increases, and this is called exponential decay. And to give you an example, looking at this one, we know that our b value is 2 for this example equation over here. 2 is greater than 1, so we must have growth. So you can see that because our function is growing as we go off to the right. In exponential decay situations, you're going to see that the function starts tall on the left and gets smaller as we go to the right, okay? All right, so applications of exponential decay we sometimes refer to half-life. Half-life is the amount of time it takes for half the original amount to remain. In problem 856, you saw this. We were talking about radioactive carbon. It takes 5,730 years for half of the original amount to remain, no matter how much we start with. And then we've also seen examples of exponential functions in general with geometric sequences. And specifically, you have to remember that for exponential functions, specifically as geometric sequences, you can only have positive integers as your input, meaning your domain can only be positive integers. That means counting numbers that are positive, like 1, 2, 3, 4, 5, etc. All right, thank you so much for listening, and I hope you have a wonderful day.